Welcome to Espresso and Electronics, quick sips of EDA wisdom. I'm your host, Anukica Sunda, and joining me today is Lance Tamura. Lance is a product management director at Cadence, and he's been in the industry for over 3 decades. Today, we are going to talk about, uh, a topic which I think everybody is going to relate to. Lance is going to talk and tell about why is everybody or why are most of the companies not building their own prototypes. He's going to talk about FPGA prototyping, the challenges and trends. So, welcome to the show, Lance.
Thank you very much, Anukica. Good to be here.
So, Lance, let's kick off this conversation. Can you provide a quick background about FPGA prototyping to our listeners?
Yes. So let's start with just some basic definitions, or what I consider the definitions of FPGA-based prototyping. So an FPGA, as many people probably know, stands for Field Programmable Gate Array, and these are large programmable devices. Actually, when I first started out, the devices weren't really all that large, and now they're gargantuan. They're millions and millions of gates. So you can implement quite large systems in modern FPGAs, the largest FPGAs that we're using today, uh, not just at Cadence, but throughout the industry. And it is a very popular methodology. However, as you said, Annika, it's not that everybody can just go out and build it. Not for the lack of trying. There are many companies providing services, providing equipment that go along with FPGA prototyping, but it is a very challenging area, both from a logistics standpoint. You have physical hardware and getting everything done, and just being able to take a design, any given design, and map it into what turns out to be not just one FPGA, but many, many FPGAs. And that's a level of complexity well beyond a single FPGA. So there's a lot of work involved, a lot of know-how that has to go into it. And the thing that it really struck me a while ago is that it it's not growing at a grassroots level because it's become too difficult. It's become too difficult in terms of the complexity to deal with, software and hardware wise. And it's also become very, very difficult to get the people, the right personnel, engineers who have those skill sets. A lot of people have focused on hardware design or strictly software design. And there's this in-between world of, well, with FPGA prototyping and emulation, well, you kind of have to walk both sides, understand both sides enough to be successful. So that's what I've seen with FPGA prototyping. It's very, very popular. If you take a look at the big picture, the big guys are all doing emulation of some sort, many of them FPGA based, and they're being very successful getting out their new devices, even though they're millions, hundreds of millions, and billions of gates large. They're able to do these things, but it's not from roll your own, build your own prototypes these days. It's really based on this class of productized platforms from different companies that are available.
Absolutely, Lance. So, talk us through what are the latest trends with FPGA prototyping.
Okay, so with FPGAs, always there's two factors. One is size, okay, and that's just a matter of keeping up with the largest designs. And if you have any experience with partitioning in a general sense, and it could be, partitioning logic on a chip, doing the physical layout, or FPGAs, it follows the same sort of dynamic. And there's a rule called Rent's rule that says you can only have so much logic going to a particular bucket, in this case an FPGA, and it's going to be constrained by the number of I/O interconnect that you have. So that's always been the challenge. We want to get the largest FPGAs, so whenever Xilinx or somebody comes up with a new device, everyone wants to jump on it because it's just bigger, and it makes the job of partitioning doable. I couldn't take a billion gate design and map it on an FPGA from 5 or 10 years ago. It would be just impossible, impossibly complex. On the other hand, I could do it on today's FPGAs because each FPGA can contain a large enough part of the design to make it practical. Down to the module and subsystem levels can start to be put into individual FPGAs even. So that simplifies the problem. So that's one thing is size. Always have to keep up with, if you look at the latest proclamations from our industry leaders, they're saying our next generation is going to be twice as big, right? They're just going massively with the technology nodes getting ever so fine now, 2 nanometer and probably 1 nanometer at some point. They're just piling lots and lots and lots of transistors onto these die. And we have to keep up with them because our job is to model their real silicon designs into an FPGA prototype so that they can do their testing and software development. The other side is speed. And this is a very interesting topic because honestly, I've been involved with emulation for a good amount of time, nearly 30 years. Emulation started maybe before my career started, but a good part of that time has been there. And it's always been about, okay, emulation is super fast. And when we say super
Absolutely.
fast, it's always in comparison to simulation. And it's been this kind of direction for the longest time. You want to use hardware because hardware can run faster than simulation. Even as simulation has improved, the hardware's improved, it's really fascinating because of that design side we talked about earlier. You could easily use a simulator to do a 10,000 gate design or 100,000 gate design. You couldn't do that 20 years ago, right? But now you can. But by the same token, there are challenges with the prototype, and you want to keep that level of performance in comparison to make FPGA prototyping worth it, because it's a lot of work and it's a lot of expense. So we want to keep that multiplier, and it's usually in the 1000x or more range in terms of performance bump compared to a traditional simulation for the largest modern designs. Very interestingly, when I was working on emulation, well, back in the early 90s, say, the number that we were always proud of was, hey, I can run my emulator at a megahertz. And interestingly, we haven't progressed that much faster than that. We're in the 1, 2, 3 megahertz range for emulators. And with prototyping, there's a bit of a kick because FPGAs have evolved, and we're talking anywhere from 4, 6, 8 megahertz kind of range. So it's not an order of magnitude, but it's significantly faster. We're actually hitting workloads on designs that are so large, you couldn't even do it on simulation. It would take forever, years, if not decades, to complete a job that, well, yeah, if your emulator FPGA prototype were running in several megahertz, well, at least you could get it in a few hours or a couple of days. So that's the two things that have driven, and this is not, by the way, a new trend. This is always how we've been pushing the limit of the technology, size and performance, keeping those two things in mind.
Wonderful. Thank you, Lance, for that insight. So, as we're talking about, the trends, what is the biggest challenge that, you see, or, like most of the people see with FPGA prototyping? I mean, is performance
Yeah.
the ultimate goal? Is it debug? What's the biggest challenge?
Okay, for me, because I've sat on both sides, both as a vendor, like Cadence, as an ED vendor, and as a user of these tools. And the number one thing we want to get done is test our chips. Okay, bottom line, we have to get products out the door with as high quality as possible, and that means running as many regression tests, so many cycles, as much software as possible before you tape out. And the thing is, FPGA prototype tend, historically, if they were created manually for the design, right, custom-made prototypes, that in itself is a huge undertaking, a huge schedule impact. I'll put it in terms of one end of the scale. We talk about some designs from, say, the military, and they're very famous for doing prototyping, right? And they build these one-time prototypes, and I've heard schedules anywhere from 6 months to a year. And they're so finely tuned and they're wonderful. They work, and then it turns out, oh, the spec has changed. Then they have to throw it out and start from scratch. That's the ultimate, oh my gosh, you've just spent a lot of time and energy. But that's how they used to do things with those designs. On the other hand, what we're seeing with commercial teams is that they're always striving for what we always call first silicon success. And if you look at the most successful silicon companies today, I could rattle off a few, the top ones. They pride themselves on really having that first silicon functional enough, performant enough to be able to sell it, right? So they can come out with their first spin, test it out. It's basically working. Maybe there are a few bugs that they can work around, but basically it's shippable. And that lets them hit their market targets, their windows, which has a huge impact on obviously their profitability. So yeah, getting these prototypes out to enable a lot of this testing as quickly as possible is important. It doesn't serve you very well if it's going to take me 6 months and ready, say, right before the tape out, you hardly got any time to test anything. So it's really, how can I more quickly bring this in? And that has led to the realization that, hey, building something custom for every single project is not practical. Also, it takes a lot of manpower, a lot of expertise, like I said, in different disciplines to get this thing done. And so the trend is moving towards standard platforms. Okay, just like emulators,
Mhm.
FPGA prototyping is also moving in that direction. Uh, you might have heard the term enterprise FPGA prototyping, and that really comes down to something that's well packaged up, just like an emulation system, but we're FPGA based and focused on performance. That second key thing that I talked about.
Absolutely. And also, Lance, do you want to touch base a little bit about like the challenges of achieving timing closure, I think, which can actually be very much time consuming when it comes to
Oh yeah,
FPGA prototyping, right?
absolutely. If anyone who's had to work on an FPGA design, even a single FPGA design, can tell you nightmare stories about how hard it is to get the place and route to meet the timing that you want, right? And there are specialty tools and doing everything. Now multiply that by all the number of FPGAs you have to do, and it's impossible. So in terms of the challenge, it is you can't overcome it. You need to rely on a big tool that understands the full system, to partition it well, and then take care of all the timing. And what we found is that companies have come with very novel ideas, technologies to make that possible. You can't do static timing analysis on a billing gate design, for example, right? You have to take some clever ideas so that it happens, that you can feed it through the FPGA police and route, and then you have an actual working system because every component can work at the speed that you want. That's super complex. So yeah, good to point that out. What I want to say is that I don't think it's humanly possible, honestly, to handle that kind of complexity alone. Even if you had a team of people, it's so complex, and your spreadsheets will blow up, right? Doing all the timing and calculations. It's crazy.
Correct. So, Lance, before we end the podcast, do you want to talk a little bit about, I mean, the move beyond prototyping, right? I mean, we're trying to move beyond the traditional role to make it a part of the central design process for advanced
Yes.
silicon, right? So I mean,
Yes.
where do you think is Cadence positioned, or like what is it that you want to, a message that you want to pass to our listeners, right?
Okay. So the important thing to remember about FPGA prototyping is this piece of silicon is by nature can run faster than other kinds of fabrics that are out there. Um, it's because of the parallelism involved. It's real logic running, and as long as you've met timing, it'll run pretty darn fast. So people need to take advantage of that and execute on their verification plans. And for the speed, what really lends itself is for software development. And I've worked, with many different software teams in the past. And the universal thing is software developers don't like to wait to run their tests, right? They want to run it when they want it, and they want the results quickly. So they need the fastest platform as possible to become productive. They want to run their test, change something, rerun it, that sort of thing. Just like you would develop software and use a compiler and run some simulation with your code. That's the usage methodology. So FPGA prototypes really are ideal for that. As far as what Cadence does, this is time to mention my product as an example of FPGA prototypes. We have a product line called Proteum, and we're in actually our 4th generation of FPGA prototypes at Cadence, and we try and address those needs to provide a platform that's off the shelf and with all the bells and whistles software to implement your design, to take away that burden from your team, and also shorten the time to get a working prototype as fast as possible. So all of that wrapped up, that's the value of, say, an enterprise prototyping system. It's not just a bunch of FPGAs on a board. It's not just some partitioning software. It's a fully enclosed hardware software system that we want to deliver to end users so that they can do their tests and they can do their software. So we can get into more details of what makes Proteum different from other products out there, but basically we've been doing it for a long time, and I think we have a very solid current generation of Proteum we call X3.
Thank you, Lance. Thank you so much for sharing your insights. It's been absolutely enlightening having you on the show.
Okay, thank you.
Thank you, listeners, for tuning in. Keep your circuits connected and your ideas flowing until we meet next on Espresso and Electronics. Stay innovative.